We're going to look at transformations of exponential functions, and so applying different numbers to the graph of a base function. So in this case, our base function is y equal 3 to the exponent x. You can create that by doing a table of values. I'm going to go from -3 to +3, but I'm actually going to fill in the table of values going backwards because my y is 3 to the exponent whatever x is. So 3 to the exponent 3 is 27. Remember, it's not 9. It means 3 times 3 times 3. 3 to the exponent 2 is 9. 3 to the exponent 1 is 3, because now this helps reinforce some of our laws, because the pattern here is divide by 3. 27 divided by 3 is 9. 9 divided by 3 is 3. 3 divided by 3 is 1. So you'll always get 1 where the 0 is, no matter what your base is. So any base to the exponent of 0 is 1. Well, 1 divided by 3 is 1/3, or 0.3 repeating. 1/3 divided by 3 is 1/9, or as a decimal, I can do 0.3 repeated divided by 3, and it's 0.1 repeating, so 0.1, on and on and on. A 9th divided by 3 is a 27th, or to get an idea as a decimal, it's pretty small, it's 0.04 if I round. So I'm going to start by putting these points on a graph. I'm actually not going to be able to fit a whole bunch on here, but I don't need a lot of points in order to do my transformation. So 3 to the exponent 0 was 1, because I'm just going to count by ones in every direction. Make it nice and easy, especially when we start to move these. Then we're just counting one space. So 3 to the 0 is 1. 3 to the exponent 1 was 3. 3 to the -1 was 1/3, which was about there. And 3 to the -2 was pretty low. And these were looked at in the last activity, that these exponentials are always these swooping curves that swoop down towards 0 on one side. And because our base is 3, or bigger than 1, it swoops up. If our base was in between 0 and 1, we'd have a graph that's swooping down. They always cross at 1, because any base to the exponent 0, remember the x value there is 0, is always 1. The domain for these is all real numbers, because it'll keep going all the way to the right eventually and all the way to the left. And the range is y bigger than 0, because only the upper part of the graph is filled up and it will never ever ever touch 0. Now I'm going to go back because I'm going to apply these transformations. So I have y equals 3 to the 2x plus 3. So now when a number is being added or subtracted inside the function with x, it's left or right and it's opposite. So this is going to move the graph left 3. When a number is multiplying the x inside the bracket, it's horizontal, and again it's opposite. Times 2 looks like it should stretch it, but it's actually going to be a horizontal compression, and you're going to take all your x's and divide them by 2. The order in which you apply transformations is you always have to do flips, stretch, and compressions first. Then you're going to do your movements. So I'm going to do my horizontal compressions, and I'm just going to get a different color. I'm going to pick a green. So I'm going to take all my x coordinates and divide them by 2. So I'll start here. The x coordinate of this point is -1. If I divide that by 2, I get -0.5. So it's pulling it in half. The height stays the same. This x coordinate is 0. 0 divided by 2 stays 0. I come to this point. This x coordinate is 1. If I divide that by 2, I get 1/2. And I get this graph that's been squished horizontally. It's like it's been pushed in from the left and from the right and squished. So the green one is that one. Now I'm going to work from the green one because I want both of these numbers to be accounted for in my final graph, and I'm just going to count every point left 3. I'm going to get a final color for my final graph. So I'm going to go from the green and I'm going to count each point left 3. 1, 2, 3. 1, 2, 3. 1, 2, 3. So the equivalent of 3 squares. And so now my swoop looks like that. So this is y equals 3 to the exponent 2 times x plus 3. The 2 squished it in, made it a little skinnier, and the plus 3 moved it left 3. Now, the domain and range of this is still the same because it's going to take a really long time, but it will keep opening and opening and opening all the way to the left. Or sorry, going all the way to the left and opening all the way to the right, and it's still y greater than 0. That's a very ugly r. For number 2, we're working with the same base function. So y equals 3 to the x. So I'm going to put those original points on it. So 0 was 1, 1 was 3, -1 was a third, and -2 was pretty low. So I use the same table of values that we worked with for the first one because I'm dealing with y equals 3 to the exponent x. Now they want us to graph a -2 in front, so -2 times 3 to the x minus 1. This is not multiplying the x. See how the x is over here and it's in front? So this is vertical. So it's going to be a vertical flip and a vertical stretch by 2. Another way to do that is just multiply all your y values or your heights by -2, and that will flip it and stretch it at the same time. So again, I'm going to get a different color and go back to my graph. So I'm going to start with a nice easy one. 1 is the height of this point because now I'm working from the y's. So that has a height of 1. And I'm doing my y's times -2. 1 times -2 is -2. 3 times -2 would be way down at -6. Can't quite fit it on my graph. This is 0.3. 0.3 times -2 is -0.6. So it's going to end up being about there. So I get this graph that's stretched, it's pulled out, and it's flipped upside down. The next thing I need to deal with is this -1 inside the bracket. So this -1, again, because it's being added or subtracted with the x, it's left or right and it's opposite. So now this means right 1. If I go to my graph, I'm going to take each point and move it right 1 square. So that's my final graph. And the domain is still all real numbers because the graph will eventually fill in left to right. But in this case, the domain is y less than 0 because the graph is under the x-axis or under where the height is 0. So for the final one, we have 3 to the negative x plus 2 minus 1. So this -1 is touching my x, so it's horizontal, but this is just going to be a horizontal flip. And then the plus 2 inside the bracket moves it left 2, and the -1 that's not in with the x, it's at the end, will move it down 1 because the number at the end, what you see is what you get. So I'm going to start with my base function, get blue. So I'm going to start with my y equals 3 to the x again. I apply all stretches, flips, and compressions first. In this case, we just have a horizontal flip, so that's going to flip it around the y-axis or side to side. So this point is at -1, so it's going to slide over to +1. 0 stays 0. This point is at +1, so it's going to slide over to -1. And I have flipped it side to side around the y-axis. So that is y equals 3 to the -x. And now all I have left to deal with is my left 2 down 1. You can do that in 2 steps if you want to, but I'm pretty confident that I can take each one and just count left 2 down 1. So from the green point, I'm going to go left 2 down 1. Go to the next point. Left 2 down 1. Left 2 down 1. And this is what I end up with for my final graph. So this is y equals 3 to the -x plus 2 minus 1. My domain is all real numbers because this curving swoop will still open all the way left and right. But in this case, my range, this is -1. So my range is anything bigger than -1 because that's the lowest point where my graph is going to swoop down to, and it's everything above that.